Hey folks, Mrs. White here, coming at you with the first lesson, section 12.1 of our last chapter of statistics. Isn't that exciting? 12 chapters. I don't think I've ever taught a math class that we went through 12 chapters in a book. I'm really impressed with you folks, and we're almost there, okay? I'm psyched, okay? So hopefully at this point you already know your test grades are up. I am not going to release your old tests with my notes on it to you quite yet until I have everybody from both classes turning the assignment in. I can't have tests out there with all of the correct or incorrect answers floating around if there's still one due. So know that your grades are up if you did turn it in on time, and I have everything annotated. I'm happy to hand it back to you soon digitally through Classroom, but I just can't do it yet until I get them all. This is currently recorded in, I don't know if it says test or exam off the top of my head, but test 4. Now, test 4 was actually supposed to be a combination of chapter 10 overlapping with 11, overlapping into 12. Because of remote learning, we decided as a whole, like dual enrollment group, that we were going to split these two tests up, but that we were going to average them both into test 4. So let's say right now on your chapter 11 test, you're rocking an 80, which is a great grade. Maybe chapter 12 is kind of weird because it's categorical data versus just like straight up numbers we've been doing for months. So maybe you get a 70, we'll say on it. Okay. So right now your test 4 grade says 80. Once you take chapter 12, it will become the average of 80 and 70. It will become a 75. Okay. So just food for thought, even though you have, whatever your chapter 11 test grade is, and for test 4 right now, it will be changing to an average of what you get for 11 and 12. And I'll put both those scores in the comments so that you know how it was averaged and you can see what you did on both independent of each other. All right. Quick summary, section 12 or chapter 12 only has 3 sections. So we'll cover one today. We'll cover one later this week. We will cover one Monday of next week, and then we're going to review chapter 12 and take our chapter 12 test. So we're looking at 3 lessons, 1 review day, and then another test. I know it's going to come very, very quick. So the reason why I'm stressing that is that a lot of people do not consistently turn in your homework. There's no quiz for chapter 12. We are done with quizzes, okay? With that being said, a lot of you use that quiz as a way to review that chapter, and then it benefited you as you looked at the chapter 11 test. You don't have a quiz. Please go through and do the homeworks. The test is 2 weeks away pretty much, right? 2 full weeks, and then it's that next Monday. So do the homework so that you're not falling behind and so that you have it fresh in your head. Okay, folks, you don't have that test to look at, to reference, to let you know exactly what things are going to look like. So let's get into it. Section 12.1 is looking at the goodness of fit test. It's not called hypothesis testing because even though we do have a null and alternative hypothesis, we're testing more than just one statistic. So we'll talk about that. It's related to the Chi-squared distribution, so we'll talk about that also. We'll discuss what is an expected count and how do we calculate it. It's nice and quick and easy. What is the test statistic we use with a goodness of fit test? Because remember, sometimes we use z-score, sometimes we use the t-score, sometimes we used chi-squared. Okay, what is our test statistic this time? And then we'll actually run our goodness of fit test, and we'll look at it with the p-value and classical. And like before, you're welcome to just focus on one or the other. If you want to do both, you will have an opportunity to fill in both on your Chapter 12 test to get additional extra points. Okay? And then again, 3 homework problems, 3, just 3, give it a go. All right, so everything in chapter 12 has us looking at different types of data than we've been looking at before now. So section 12.1 has us doing the goodness of fit test, which we use when we're trying to determine and make calculations related to distributions. So in the past, we didn't look at an entire distribution. We looked at like one portion and compared it across samples. So for example, maybe if we're thinking of M&Ms, we would say like in a, family-sized M&Ms there's 10% reds. Is that different in the proportion of reds in the fun size, right? Because fun size is not actually fun, it's small. So you have the big bag, 10% are red, and the small bag, is that different? So our null would be that they are not different, and our alternative would be that they are different, which means not equal to, okay? Now, if we are doing a goodness of fit test, what's going to happen is we're going to be given the entire distribution for all of the colors. So it might say something like, well, yeah, in a bag, 10% are supposed to be red. 15% are going to be green. 29% are going to be black. And let's see, we got yellow. I don't even know what colors I said, but you can imagine we would have all of the percentages for all of the different colors of M&Ms, and we would be comparing the entire distribution, okay, to determine if it is the same or different. Not just one color, not just red, but looking at the entire distribution for something and determining, is it the same or is it different? Is there a change? Is there not? Okay, did things increase? Did things decrease? So you will be having to write null and alternative hypotheses. Most of the times, these are going to be dealing with words more so than letters and numbers. And we'll see a handful of examples for that. But if we think of kind of like a dice, because this one's kind of straightforward, okay? If I was asked something like, is a dice fair? Yes or no. You're not really looking at the probability of rolling a 2 or rolling a 3. You're looking at the probability of all 6 sides, right? So if we're deciding if a dice is fair, our null hypothesis is that all of the sides are the same, right? All of the probabilities of rolling each side is going to be identical. So the probability of rolling side 1 is going to equal the probability of rolling a 2, which is going to be the probability of rolling a 3, and rolling a 4, and you can see where I'm going. The probability of rolling a 5 and a 6, but we don't just stop there because we actually know what this distribution would be, right? It's going to be 1/6. So in order for something to be fair, we would assume that it's fair, right, until we have evidence that it's not. We would say that all of those pieces, all those different probabilities or proportions even, should be 1/6. They should all equal each other. In this instance, our alternative would be that at least, and we wouldn't have to write it out like this for our alternative, we would say at least one side is different. We don't care if all of them are different. If one side is different, then we know that it's not a fair dice. Okay, so our null is that it's fair, our alternative is that it's different. And you'll see that in the 2 examples we do today and some of the other null and alternative hypotheses in the other sections that we end up using words a lot. Another thing would be we could look at like comparing population spread in the US. Okay, this is another example from your book that's pretty good. We could say something like, I don't know, from the census back in 2000, maybe like 19% of people are in the Northeast. Let's say 22% are in the Midwest. Okay. And then we have that 35-ish% is in the South, 22.5 is in the far West. Okay. So we end up getting a distribution of population across the country. And I didn't write them all in. I was kind of, like I said, I'm following along from some good examples they have in the book. If we're thinking about that, we have that each of these proportions, it's not that they're all equal, right? It's that they have their own values. So if we're trying to see if from 2000 to 2010, because they do the census every 10 years, if the population changed or increased, our null would be that they aren't, okay? So there's no way to write that these percentages didn't change in a mathy language, right? We're not saying that they're all equal. So we literally would write our null statement being that the population distributions, how people are distributed, right? The population distribution has not changed. Or we would maybe say is the same. In 2010 as 2020. Or 2010 as in 2000. We don't have the data for 2020 yet, obviously. Okay. Our alternative would be that the distributions are not the same. Okay. So just to save me from having to write it, it would literally just be that instead of it is the same, we would say that it's not the same. And that's what we would be testing here because we're looking at even just one of those being different means that they are not equal. okay? Just like one of these sides could be different and then they're not equivalent, okay? Here, if we were doing the same sort of testing, if it was significantly larger or smaller, right, we would say the proportion of, every single color from our big bag to our little bag, then that's going to be accepting that alternative hypothesis. So these feel a little funky at first, but we'll get used to them. The calculations that we do for the goodness of fit test are focused around the chi-squared distribution. So I just want to show you that again, because if you're contemplating using the classical method, it helps to kind of see the graph. And how we're going to be using that graph, being that it's not symmetrical, that the shape changes depending on the degrees of freedom, okay, kind of like the student T distribution getting a little bit taller or shorter, but this one it changes a lot. As the degrees of freedom are higher, it becomes almost more symmetric, right? It almost starts looking like that normal curve. And that your chi-squared values are non-negative, right? The lowest value that we have here is 0. So when you're sketching this out for classical, you're just doing your positive quadrant, and then we have it come up and then kind of taper off at the end. Usually with our chi-squared, specifically for these tests, they're all going to be located as shaded to the right. Okay, and that'll be how we kind of sketch that out and kind of refresh our memory on that. That also lets us know a little bit about our test statistic, right? If we're dealing with a chi-square distribution, that's going to be what our test statistic is going to be based off of. So before we can even do some of these calculations, since what we're doing is comparing two entire distributions, we need to be able to do a handful of quick checks, and we need to be able to understand what an expected count is. So right from the book, just like normal, we'll take a quick look at this. So suppose there are n independent trials of an experiment. With k is greater than 3 mutually exclusive possible outcomes. So what that means, folks, is as we're looking at our tables, okay, it has to have at least 3 non-overlapping outcomes, okay? So it's not what we did last chapter. Chapter 11 had exactly 2 outcomes, right? Just 2 outcomes. This is going to be that it has 3 or larger non-overlapping outcomes, okay? So P sub 1 is going to represent the probability of observing the first outcome. So I kind of previewed this with you in our SITMIGAN, right? Here's our first outcome, here's our second outcome, here's our third. We would do a goodness of fit test here because we have 3 or more groups. Otherwise, we would just do our normal hypothesis tests for 2 samples because we only have 2 numbers, okay? So then E sub 1 would be the expected count for your first outcome. And then it kind of just goes on for that. So that's just kind of so you can understand the outcome. So this capital E is not going to be your margin of error right now. This is going to be your expected count. And they're using the delineation of I, saying that I would be the highest amount that you could have, okay, or you're going to have. So to get your expected count, it's actually very easy to calculate. You're going to take your n, which is your sample size, and you're going to multiply it by your expected probability, okay, which is your expected outcome, all right? It's pretty darn quick, pretty darn easy, and we'll do a couple examples of it. And you'll have several of these, right? This isn't one calculation. You're going to have it when I is 1. You're going to have a number for when I is 2 and another number when I is 3, all the way out until you get to however many different groups you have, okay? Remembering that K represents how many groups you have, how many different outcomes there are. So if I was writing this in notes, I would make sure to put expected counts equals a capital E, that it must be greater than or equal to 3 categories. Okay, the E isn't, but that, well, maybe we'll put a little semicolon in there to delineate that. So it has to have more than or equal to 3 categories that are non-overlapping. That's what mutually exclusive means, okay? And that to calculate this, we are going to do our n times our pi, okay? Which is going to be how we get to our expected count. So let's just calculate an expected count. Like I said, it's pretty darn quick and easy. One growing concern regarding the U.S. economy, and this is on the sheet. If you printed it out, then you want to make sure to grab it right now. This example is on there for you. One growing concern regarding the U.S. economy is the inequality in the distribution of income. The data in Table 1 represents the distribution of household income of various levels of income in 2000. So what they did is they took raw numerical data that we could have done other tests with, and they broke it into categories, right? So we have under 15,000. 15 to almost 25, 25 to almost 35. Like, because this is not raw data right here, folks, this is why we end up doing our goodness of fit test. And if you look, 1, 2, 3, there's more than 3 categories here, right? There's actually 4, 5, 6, 7. There's 7 different categories here. So we're testing this entire distribution, okay? So anyways, an economist wants to know if the distribution of income is changing, so she randomly selects 1,500 households and obtains their income, find the expected number, so they're telling us find our expected number of households at each income level, assuming that the distribution of income has not changed since 2000. So we're going to use this exact data to calculate our expected incomes, all right? So if we're doing our expected income for our first category, okay, so I'll put a little 1 here that will delineate that this is for our first category, okay. I'm going to do my n, which is my sample size, times the proportion of getting that specific value, okay. And here I'm not going to necessarily put a 1. I'm going to put that this category name, because I'm not trying to get a 1, is going to be under 15,000. Okay, so my little sub here becomes the actual label that I'm looking at. So if I was doing M&Ms, this would be P red, P blue. Okay, this is P under 15,000. Okay, so our N value they gave us, it's 1,500. Oh my goodness, my pen. And I'm going to times it by the probability of having under 15,000. Well, they already told that to me. It's 7%. So I'll move that decimal point forward 2 spaces, add a little 0 placeholder there, and I will do my n times my probability of under 15,000, which is 0.07. Okay, and that's going to give me my expected value for my first category. And if I actually took a second and multiplied that, I should get 105. Okay, so my expected values, and I'm going to put a little sub I here to imply that it's all of them. This one's going to be 105. Okay, I'm going to go through and do the second one. I'll write it all out. The other ones will just actually do the math. So we're going to look at our second category. That's going to be our sample size times the probability of 15,000 to 24,999. So 15,000 to 24,999. And that's going to be, again, our sample size, 1,500, times the probability or the percentage of that actually occurring. So I'll move this forward 2 spots, okay, because I want to make sure it's a decimal. And I will do 0.086. So I'll take that 1,500, times it by this, and I should get 129. Okay, 129. Now, if I continue through each of these categories and do that same calculation, I will get these values just to kind of finish up solving this problem. So I move this one forwards twice, times it by 1,500, and I'll get 139.5. I would move this forward 2 places, so 0.143 times that by 1,500, and that's going to give me 214.5. And then I'll keep going, move this forward to 0.197 times it by 1,500 for my n, and I'm going to get 295.5. 2 expected values left, so I'll move this forward twice, do 0.15 times 1,500, now I'll get 225. And then the last one is going to be, move it forward twice, so 0.261. I'm going to times that by 1,500, and that's going to give me 391.5. So that is all of my expected counts that I should get. So based on this sample size, If 7% of people should be in this category, that's going to be 105 people. Okay, that's what this means. That's what the expected count is. So if the percent of people are 8.6% and there's 1,500 households, I should expect 129 of those households to have an average income between $15,000 and $24,999, and so on and so forth. So when we took this probability of it happening, or the percentage of it happening, and times it by our sample size, this is what we expect to see if everything is the way that it should, right? If there's no change in the incomes, then this is what those groups should really look like. Okay, and that's, again, the definition of expected counts. So expected counts is going to be part of our test statistic, and it's going to be part of the calculation that we have to do to run the goodness of fit test. So the test statistic, like I said, for the goodness of fit tests is going to have to deal with our expected values, okay? And it's also going to be the actual observed ones. So often, out of those samples, right, if we think back to this example, there's probably not going to be exactly 105 households that are there. It might be a little bit more, it might be a little different, okay? For example, 139.5, you can't have half of a household, okay? So it would make no sense to have that 0.5 there. That's going to be either larger or smaller, okay? Similarly, these are your expected. This is kind of like what you would expect to happen theoretically. Remember when we did that with probability, okay? And then your observed counts is like if you actually did the experiment. That would be, for us, that would have been the experimental probability. So this is what we expect to happen, and this is what actually does happen. So we are not going to calculate this by hand. We have a calculator that's going to do it for us, but I want to talk to you about what we would have to do by hand so that you can appreciate your calculator just a little bit more. So I want to point out that this is the summation symbol, which means that you would do this ratio, this little fraction, over and over and over, and then add them all up. So you take your observed count, okay, you subtract from it your expected count that goes with that exact same category. So once you find the difference, you square it, and then you put it over your expected count. So it becomes a division problem in a decimal. You find that value, you add to it your next one. So you take your observed count of your second category, subtract it from the expected for your second category, get that difference, square it, divide it by your expected, add it to the third, and you go all the way through until you get to your kth category, remembering that there has to be more than 3 categories. That's one of our things that we had discussed previously. So this is the calculation for our chi-squared, which is what our test statistic is for our goodness of fit test. So when it asks you for the test statistic, we're dealing with chi-squared. All right? So important to note, and you'll see when we do the classical that this comes into play, you're going to be doing k minus 1 is going to be your degrees of freedom. So what that means is your degrees of freedom are based on the amount of categories you have. So you're going to look at how many categories you have, subtract it by 1, okay? It's not based on your sample size, it's based on your amount of categories is your degrees of freedom. Now, normally we would check to see if things were normally distributed before being able to run a test. We're taking into consideration a couple of these things, and these are the 2 things we're going to check every time before we start doing our hypothesis testing or our goodness of fit test, because that's what it's called when we're comparing different categories. The first thing is that we need all of the expected frequencies, so all of these are expected values, to be greater than or equal to 1. Okay, so we can't have an expected value less than 1. If you do, you can't run the goodness of fit test. Okay, all of them have to be greater than or equal to 1. Now, our second one, no more than 20% of the expected values are less than 5, okay? So you can have 20%, you can have 1/5 of your expected values to be smaller than 5, but the rest of them have to be greater than it. So you're just going to check these 2 things every time, and that's one of the things you just have to kind of memorize, okay? In some problems, in the first one, we're not going to have to calculate our expected values or expected counts because we already did it. They're going to provide it for us. But in our second example, we are going to have to do that in addition to doing just the observed counts, okay? Because we're going to have to plug these in and these in. This is going to be an L1, L2 situation, okay? So we're going to have to check first, are all of our expected frequencies greater than or equal to 1? and are no more than 20% of them smaller than 5. Okay, so 1/5 of them smaller than 5. So the goodness of fit test should feel pretty similar. I did put these steps up for you so we could talk about them briefly, just because it does look a little bit different. So I always like to verify these things first, but they always throw your hypothesis, developing your null and your alternative first. So your null is always going to be that there's a certain type of distribution, okay? So the word distribution is usually going to be in there. They're going to give you some information about this, okay? And we'll make sure that we can start working on identifying that from the word problem. The second thing, your alternative is always going to be that it just doesn't follow whatever that first distribution is, okay? That's always going to be our null hypothesis. And like we saw when we talked about those 3 situations in the beginning of this lesson, that sometimes these are written entirely as a sentence, okay? And no mathy letters and numbers involved in it, depending on what we're looking at. Next, you have to decide a level of significance depending on the seriousness of making a type 1 error. So usually they're 5%. It could be 5%, 10%, or 1%. We don't want to do anything rando. And then our third step is going to be that you have to calculate your expected values, okay? That's something new. You don't just start plugging stuff in. You're going to have to go through and calculate those because they're going to become something that you have to input. So memorizing that little formula that we were just doing in the first example is going to be really important. It's not hard to do, okay? And then remembering that your degrees of freedom are based off of your actual amounts of categories, okay? So once you do that, you've created your expected counts. You want to make sure that those expected counts, right? And that's why they have this listed down here versus up top. Okay, that was my mistake in referencing that. Usually we do it first, right? But here, because everything's based off of expected counts, we have to calculate them, okay? So we have to make sure that all of the things we did in part A are all greater than or equal to 1, and that there's not too many numbers that are less than 5. So you can only have 1/5 of your numbers or 20% less than 5. So let's actually go through and do this, and we'll make sure to write down the keystrokes. We'll do it using p-value and classical method. So here's the exact table we were just looking at, okay? But we first saw the decimal values, and then we calculated the expected counts. So these are the exact expected counts that we calculated previously, okay? So we'll just read over the problem one more time. One growing concern regarding the U.S. economy is the inequality in the distribution of income. An economist wants to know if the distribution, so see how they're saying that they want to know if the distribution, that's cluing you in that we're going to be doing a goodness of fit test. If it mentions distribution, it's going to be goodness of fit. And if you have more than three or more categories, that's going to clue you into goodness of fit. So they want to know if it's changing, okay? So she randomly selects 1,500 households and obtains a household income shown in this table. Table 2 also contains the expected counts under the assumption that it has not changed, okay, which would be our null hypothesis. Does the evidence suggest that the distribution of income has changed since 2000? So again, they're saying the word distribution. That's letting you know goodness of fit test, okay? So we're going to check our 2 things first, mainly because we already have our expected counts, right? Here's our expected counts. So our first thing here is, are any of these numbers less than 1? So are any of our expected values less than or equal? Or actually, we want them to be greater than. So maybe I should write it the way that we want it, right? We want them to be greater than or equal to 1, and every single one of them is bigger than 1. So we're good to go. The second thing is we want to check and see if any of these are going to be smaller than 5. So there are none smaller than 5. So number 2 is automatically good, but we would be checking for 20%. Okay, so we would do 20% of 1, 2, 3, 4, 5, 6, 7. So that would be potentially 1 or 2. If only 1 or 2 of these were below 5, we wouldn't be able to do this test. This would make it so that you couldn't, and you would just say, cannot run a goodness of fit test. However, none of them are less than 5, so we're good to go. So both of these are met, both of these assumptions. So I'm ready to start thinking about what I'm going to do for my hypothesis, or my null hypothesis, and my alternative hypothesis. Okay? So to start off, I look back at that wording, and the wording is that it is changing, okay? So our null hypothesis is going to be that it doesn't change, okay? So you might be saying to yourself, all right, so how can we write that mathematically? We're not going to worry about this. We're dealing with categories, so it's perfectly fine to have some words involved here. If everything had the exact same probability of occurring, then it would be something different, right? Remember the dice in the first one, how they were all 1/6? That would be different for our null. However, here we know that they all had different percentages, right? And so we're just going to say that the null hypothesis is that the income has not changed. That would mean that our alternative hypothesis is going to be that the income has changed, and specifically that only one of these has to be changed, okay? Significantly, right? Statistically, significantly, only one of them needs to have changed for it to be an issue, okay? So we'll put at least one income has changed. Maybe they've all changed, who knows, okay? But if at least one has changed, then the fact that none have changed, okay, would be kind of rejected. So what's nice is that the majority of the work we're going to do, especially if you decide to just focus on the p-value, is all on your calculator. So nothing's really changed there. They mentioned that our alpha value is going to be 0.05. So I'm going to go into my calculator. I'm going to go to the stat menu. And hopefully you're assuming that we're going to the test menu, which we are, because this is a type of hypothesis test, right? We're still developing a null and an alternative. Then we're going to think, what is our test statistic? Well, that's chi-squared. And then we're doing the goodness of fit test. So we're going to go stat test. We're going to find the one that says chi-squared GOF test. GOF standing for goodness of fit. So let's see. I think I have my graphing calculator here. So I will go into stat. I'm going to go over to tests. And then I'm going to scroll down till I can find chi-squared. Okay, so I have the chi-squared test, but I want more than that. I want the chi-squared goodness of fit test right there. Okay? Now, in order to do this, I have to have my observed data in L1 and my expected data in L2. I also need to plug in my degrees of freedom. Okay, and remember, degrees of freedom when we're dealing with this categorical data is the amount of categories, our k, minus 1. So let's go back and we'll plug in all of our L1s. So if I'm looking right here, my observed should go in, and this is observed, should go in L1, and my expected should go in L2. So feel free to grab out your calculator and plug those in. I'm going to take a second and actually type them in on that graphing calculator so we can run our test. All right, now that I have all of my expected values in my L2 and my observed values in my L1, I'm ready to go back in and run that test. So again, I'm going to go stats, I'm going to go over to tests, and I'm going to go down to chi-squared, which lets me know that's my test statistic, but I'm going to go over to chi-squared GOF for goodness of fit test. My observed is in my L1. My expected is in my L2. If we look back at the original problem, I think there was 7 categories, right? 1, 2, 3, 4, 5, 6, 7. So my degrees of freedom is going to be 6. And I'm going to go down, and I'm going to calculate. So you can see here it gives us information that we're looking pretty good about, or pretty confident about. Chi-squared is our test statistic. So we're going to do 10.1053. Our p-value is 0.12, and we already know our degrees of freedom is 6. And that's all we really have to worry about on the screen at the moment. So we'll record those in here. Our test statistic. again, remember, your test statistic is just a vague name for whatever it is that your test statistic is, and in this case, it's that chi-squared measurement, and that was 10 point, let's see, 10.1053. So let's write that down, 1053. So I would use that mainly if I was doing the classical method, which I'll do over here. But for now, let's just stick with the information we just calculated. So if we're looking at our p-value, we got that our p-value specifically is 0.12. And we want to make sure that that is less than our probability of making an error, right, which is 0.05. So is this less than 0.05? The answer is no, it is not. So no, there is not enough evidence to accept the null. Instead, I'm going to there's not enough to accept my alternative, so I'm going to be accepting my null. Okay, I cannot reject it. I'm going to keep it. So this is saying that the income has not changed because we're at a no. Again, we're looking at this whole distribution, right? We're looking at the distribution of our income. And even though it does look different, right? This and this are different, this and this are different, all of these are different. The general distribution actually is not different enough for us to say that it's changed. It hasn't changed, okay? If we were to look at this doing the classical method, excuse me, we're going to first sketch out not the normal curve. Again, we're dealing with chi-squared, right? So we're going to do this distribution. Now, usually we worry about left, right, or two-tailed. When we're dealing with a goodness of fit test, we are always dealing with it being right-tailed. So we have to find chi-squared for our level of significance, which is 0.05. And once we know what that chi-squared value is, we can see, is our test statistic right here in this shaded region or is it not? If it's in the shaded region, yes, there's enough evidence. If it's not, no, there's not enough evidence to accept our alternative. So to do this, we're actually going to have to go to table, I think it's table 8 in your book. I do have it up. We'll take a quick look at it. It's going to be on page A15 for you folks, and it's also in the insert that I've linked to you folks in the past. So let's take a quick look here. So table 5, 6, 7, 8, chi-squared distribution. So we come over here, degrees of freedom is 6. I'm going to go over to 5%. It's going to be 12.592. So this value is 12.592. And my question to you is, where's 10? 10 is over here. Is it in the shaded region? No. Is there enough evidence then? No. Okay, so we end up with that same conclusion. No, there is not enough evidence at a 0.05 level of significance to say that the income has changed. Okay? There's not enough evidence to say that the income has changed. Let's do another one where they don't give us the expected. So this is like as hard as these are going to get. Okay? So, an obstetrician wants to know whether the proportion of children born on each day of the week is the same. That right there is letting you know your expected. Okay? That the expectation is that all of these probabilities for each day of the week is the same. She randomly is going to select 500 birth records and obtains the data shown in Table 3, based on the data obtained from vital statistics of the United States in 2012. Is there reason to believe that the day on which a child is born does not occur with equal frequency? So we're testing, are they equal or not? Okay. So before we go through and do too much, we're going to need to figure out our expected values for each of these. So we'll start right here. Remember, the calculation for this is n times the probability of it occurring. So if you think about this, we want to see if they have the same probability. So the probability of you being born on a Sunday would be 1 out of 7 options, right? And the probability of you being born on a Monday would be 1 out of 7 options. So all of these actually would have that 1/7, okay, that 1/7 as the probability of it occurring. So all of these are actually going to have the exact same expected value because expected value is our n times the probability of whichever category we're looking at. All the categories have the exact same probability of 1/7 occurring, right? That's the probability of each day occurring. So they're all going to have the same expected value, and that's perfectly fine, okay? If you're looking at things being the exact same, so if we were doing like that dice problem again, everything would have 1/6. You would look at your n value, you would do your n times the 1/6, and that's going to give you your expected value over and over and over. Okay, because if they're all equal, then they should all have the same expected value being equivalent. So let's start by, we really just have to calculate one of these. So we'll do 1/7 times 500. That 500 would technically be over 1. So it's really just 500 over 7. Okay, and we could divide that out real quick. We'll just round it to 71.43. Okay, and that 71.43 is going to be the exact same for each of these, right? Because we want to see if they are, the probabilities are exactly the same. So after I write these in, I'm going to hop right over to thinking about my two important pieces and parts to be able to actually do a goodness of fit test. The first thing I'm going to ask myself is there any values in my expected values that are less than 1? And the answer is no, there's none of them, so that's good. The second thing, are there any numbers less than 5? And if there are, it can only be 20%. So 20% of 7 options. Again, one option would be 7%, so 2 options would be 14. So it'd be 2 options could be below 5, but none of them are below 5, so that's fine. Okay, now I'm ready because I can run the test. I have my expected, I have the observed, right? The frequency in which it actually occurred is your observed. I'm ready to write my null and my alternative, and then I'll hop into my stats test menu. So my null, and this one's different than the other one, is that every day has the same probability. Okay, so this could be modeled because everyone's the same, is that the probability of Sunday is going to equal the probability of Monday, which is going to equal the probability of Tuesday. Hopefully you're figuring out where I'm going with this, which is going to equal the probability of Wednesday. Whew, more than halfway there. Probability of Thursday. Probability of Friday. Probability of Saturday. And that all those probabilities should equal 1/7. Okay? Now again, if they have to be the same in order for it to be our null, then our alternative is that they're not the same. And more specifically, that just one of them is not the same. And that's what I'm going to write. So I would say at least one day is not the same. Okay, so null, alternative, I'm ready to run my statistical test. So I'll come over here. Now before I even try to run this, remember I had to put information in L1 and L2. So let's go to our stat menu first. We'll go right into edit. And let's clear each of those out. And then we'll just take a second. You can do it too. We'll just plug in our current values into it. All right, now that I have each of these plugged into L1, L2, I'm going to go in and run my statistical test. So I'll go into stats. I'm going to go over to tests. Oops. I'll go back into stats. I'll go over to tests. Then I'm going to go down till I find my test statistic, which is chi-squared. And then I want to do the goodness of fit test. What just happened? There we go. I'm going to make sure I do have my observed in L1. I do have my expected in L2. There were 7 days of the week, so my degrees of freedom is still 6, and I'm ready to calculate. So I get that my chi-squared value is going to be 19.5676, and that my p-value is 0.003. So I'll write both of those down now that I'm here. So my test statistic is chi-squared, and it was equal to 19.5676. If I think of my p-value specifically, my p-value is 0.003. Is that less than 0.01? So this was, they're taking it pretty seriously, right? Like that 1%, oh no, only a 1% error. I mean, that's very small. Okay. So is 0.003 less than 1%? It actually is. Yes, it is. Okay. So that would mean, yes, there's enough evidence I can reject my null and accept my alternative. Okay. So we would say that, there is enough evidence at a 0.01 level of significance to say that students are, or not students, that children are not born equally on each day of the week. Okay. Or the probability of them being born equally on each day of the week is not the same. Okay. Either of those would work. If you were going classical, you would go, you're going to have to sketch out your little chi-squared graph. Remembering that when we do our goodness of fit test, we're always doing a right tailed test. We're going to go over to our insert. We had 6 degrees of freedom. So we're right here, and we're going to follow it all the way over to 0.01. So 16.812. So this number right here is 16.812. Our test statistic was 19. 19 is in the shaded area. If it is in the shaded area, there is enough evidence to support your alternative and reject your null. Okay, so we end up with the exact same conclusion. When we get to the actual crunching of numbers, this process isn't that hard, right? I think the trickiest part is writing your null and your alternative. So make sure you take your time and use the wording that's either in the problem or in the question itself to be able to help guide you as you write those. If writing those or any of the homework problems are tricky for you, I would encourage you to check in with me during office hours. We only have 3 sections left, right? So even if you wanted to just come to office hours and do all 3 of them with me, you'd get credit for the homework and it'd help you out a little bit, okay? You get a little bit extra studying in. Otherwise, I'm good to go if you're good to go. I will talk to you folks later. Have a great one.